In this video, we will introduce the concept of the differential. So if we're given a function y equals f of x, then there's going to be two differentials. We think of the differential dx as being an independent variable. And in a few application problems in a moment, we'll see exactly what we mean by this. But basically, it's just saying that dx can take on any value we would like. Then the differential dy is defined in terms of both x and dx by the equation given here. And note, just from an intuitive perspective, what we're saying is that if y equals f of x, dy dx, the derivative of y with respect to x, is f prime of x. So what we are doing here in essence is saying that we don't have to think of dy dx as being a single entity, but instead we can think of it as two separate parts, a dy and a dx. So to get the differential dy, you just multiply dx over to the right. So really, if we want to find the differentiable of a function like y equals the square root of x squared plus 3x, what we do is we differentiate the function and then simply multiply it by a dx. So let's go ahead and find the differential for these two functions. So in order to find the differential, we first need to differentiate the function square root of x squared plus 3x. This will be a chain rule problem. The inside function x squared plus 3x, the outside function which is the square root. And let me remind you of a differentiation formula that we encountered. The derivative of the square root of x is 1 over 2 square roots of x. And this is something that we found using the definition of the derivative back in a previous example, but also note that you could come up with this using the power rule. Square root of x is x to the 1/2, so the derivative is 1/2, which comes down forward, and the new power of x is 1 less than which was previously there. So 1 over 2 x raised to the 1/2, 1 over 2 square roots of x. So in order to differentiate the given function, we're going to use the chain rule. We differentiate the outside function, which is a square root, so 1 over 2 square roots. We evaluate it at the inside function, and then we multiply it by the derivative of the inside function, 2x plus 3. And then to get the differential dy, what we're doing is we have f prime of x, we've differentiated the function, and then we simply need to multiply that by dx. Let's do the same thing with this second function, y equals cosine of the quantity x squared plus x. Once again, the observation is looking at the x squared plus x inside the cosine. This derivative is well suited for us to use a chain rule problem. So dy, to differentiate, we take the derivative of the outside function, which is minus sine. We evaluate at the inside function, x squared plus x. We multiply by the derivative of that inside function, by the power rule, 2x plus 1. And then we put our dx. Now let's think about what the differential is really giving us from more of a geometric point of view. So I think of the following picture with the geometric interpretation. And how I want to think about this is I'm sitting on my curve. We have the function y equals f of x in blue. And at this point A, I'm thinking we're at the input x. And what I would like to know is if I change that input slightly, that is, if I let delta x be the change in x, which I set to the equal to the differential dx. So dx is going to be some small number which represents how much we change x. I would like to know when I change x, how much does my function value change? So the delta y in this problem represents the actual change in y. And what the differential dy is going to represent Well, we've drawn this tangent line at this point A. The slope of the tangent line is f prime of x, which we think of as dy dx. So we think of this as being rise over run. So the dx is measuring, how far we go over, and the dy is measuring how far we go up on our tangent line. So the observation to make is that the differential dy is this quantity over here, and then delta y, the actual change in y, is going to be approximately the same value. Clearly they're not the same, there's this small difference here, but as we make this change of x smaller and smaller, we get a better and better approximation. So the main idea from a geometric perspective is that the differential dy is going to allow us to approximate a change in y. And that approximate change in y is going to depend upon an x value, the value where we are at, and it's going to depend upon how we're changing. So it's going to depend upon that differential dx as well. So I realize that this is a rather abstract idea. Let's see if we can see how it works through a few examples. So use differentials to approximate the increase in the surface area of a soap bubble when its radius increases from 3 to 3.025 inches. So we're told to use differentials to see how the radius increases from 3 to 3.025. So first of all, let me just think, what is the surface area of the soap bubble? So I'll say it's area A, and the surface area of a sphere with radius r is 4 pi r squared. And what we would like to do here, we're thinking of the A maybe as playing the role of y in that previous example, and r is playing the role of the x. So if we change the r value from 3 to 3.025, so we're thinking of r as being 3, and then dr is going to be our small change in r. It's changing from 3 to 3.025, so 0.025. So the differential dA will approximate the actual change. So dA is going to be the derivative of 4 pi r squared. We're thinking r is our variable. So the 2 comes down, so 8 pi. Our new power of r is 1. And then we multiply by dr. So we have found the differential dA. Now note the differential dA is approximately equal to the change in the surface area. It doesn't give us the actual change, it just approximates it. So what we would like to do is find that approximate change when the r value is 3 and we're changing the r value by 0.025. And so that's the key there. We want to find the approximate change in the area when r is 3 and we're changing r by this small amount, 0.025. So we plug into our previous formula. So this dash that goes with the r was a 1. And so we're plugging in 1 to the first times we're plugging in 3 for our r and multiplying by 0.025. So this gives us 24 times 0.025 pi. And if you plug this into a calculator, it becomes, well, let's actually not plug it into a calculator. Let's just say if we evaluate 24 times 0.025, a quarter of 24 is going to be 6, and then a 0.0 makes it 0.6, times pi, and the units here will be square inches. So this is an ideal example showing us how we can use a differential to estimate a small change. Let's look at one more such example. The edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeters. Let's use differentials to estimate the maximum possible area in computing the volume of a cube. So the idea here is that we have a cube, and that means that each side of this cube has the same exact side length. Let's call it x. And we measure it, and we find that the x is equal to 30 centimeters. But we're told that there's a possible error in measurement as much as 0.1 centimeters. So we're thinking there could be a small change in that x value, so the small change is dx of 0.1 centimeters. And what we would like to know is how much would that possibly change the volume of the cube. So the volume of the cube is going to be x cubed, and we want to think, how does this small change in the x value affect the volume? So what would be the approximate change? Well, the approximate change would be given by the differential, dv, which would be 3x squared dx. And we want to know the value of dv when x is 30 and dx is 0.1. So we substitute in x equals 30 and dx is 0.1. So that will end up being what, 2,700 divided by 10, which is 270. And the units to go with this will be cubic centimeters. So if we change the length of one side of the cube by at most 0.1 centimeters, the volume of the cube can change approximately up to 270 cubic centimeters. So a very interesting example.